So first, let me thank Google and everybody for putting this together, putting this whole thing together. I'm very honored to be at the center of it. But it's very nice to see all these people that I've known and met and had students and so forth over the years. But Ludmil, I have to do what Ludmil says, and of course he invited me to give these two lectures. I gave one on Friday, where some of you, of course, haven't heard it. But my reason for choosing the topics is the following: that this conference is supposed to be about 50 years of my mathematics, and so these are the first two papers that I published in 1974. One of them is on spinors, and that was the topic of my talk on Friday. The other one is on four-dimensional Einstein results, and that's the topic of my talk today. So my guide as to what I should be that. So these are, so today I'm going to talk about ALE states. And so let's start with the picture. So we're going to find out subgroup of SU2, and we'll look at the singularity, the quotient singularity of C2 over gamma. Then we know that we can resolve that, and what we get is a configuration of exception curves, rational curves, which intersect according to Lincoln diagrams of type A, B, E. And these diagrams correspond to the different types of finite subgroup, where the quotient by the center gives us a subgroup letter 3, so it's cyclic, dihedral, tetrahedral. Octahedral, icosahedral, corresponding to AB, E, 6, E, 7, 8. And in 1989, well, this was basically Kronheimer's thesis. He gave a very beautiful construction of metrics on these, complete hyperk metrics on each of these resolutions, these complex, non-compact, complex sets. How did he do it? Well, so what did he give? Anyway, he gave us this. He gave a complete Riemannian metric, asymptotic to the flat metric on the quotient of R4 by this finite group. It has the property of being hyperk. So holonomial is SU2, or you might think of it as quaternionic. So tangent bundle has these reactions of quaternions on it, and there's a metric with respect to which I, J, and K are complex structures, making it a Kähler metric. That means we have these three Kähler forms, and we go 1, 2, 3. And he produced lots of facts about them. In particular, the moduli are essentially given by the periods of these three forms. So we have this K. K is the rank for the algebra, and so we have a 3K invariants, which are the periods of these three forms, and they're the moduli. And the construction was by the hyperk quotient construction. So this is how it goes. If you start with the ALE singularity, and you take a group, finite group gamma, and you look at the L2 functions on gamma. So that's the regular representation. Then you look at the endemorphisms of this Hilbert space, this finite dimensional Hilbert space. So that's a real space. You have the adjoint action in it. So then you take the tensor product with C2, which is the quaternionic vector space. So the quaternionic tensor real quaternionic. You take the gamma invariant part of that. So that is a vector space. If I call it M, because we've got a manifold here. And then there's a group acting on this, which is the group, the unitary group of this regular representation, and you look at the gamma invariant part of that. And of course, the regular representation splits up into irreducibles, and so this gamma invariant part is a product of unitary groups corresponding to those irreducibles. So we've got a quaternionic vector space, and we've got this group acting on it is preserving the quaternion structure. And that's all set up for the hyperk moment instruction. So there's a moment map. So for each of these two forms, these symplectic forms, there's a moment map into the field of the algebra. Well, the algebra has a metric and variant metric on it. But there are three forms, three Keller forms. That means you have three such maps. So there's a map into R3, tends to be with the algebra. And there's a choice here. So there's a choice because each one of those unitary groups is a center. You can always, in order to have an equivariant moment map, then you can always change it by something which is invariant under the action. So you have a choice depending on the unit, the center there. So you have k degree, k choices, well, k choices for each omega, which means 3k choices there. And those 3k choices are the same as the moduli. It's equivalent to the periods of those three two forms. And the hyperk quotient construction tells you that you look at the inverse image of the moment map and divide out the action group. So it's very beautiful and it fits very well with the picture. And okay, so here's the situation. So we take E8, we take the icosahedral group. Then the dimension of this, the real dimension of this vector space is 480. So this is, if you like, this is just linear algebra in the sense that the abstract of the ADHM paper was just linear algebra. But what kind of linear algebra is it? So it's a 48-dimensional space with 357 quadratic equations in it. So you have to solve 357 equations with 480 variables and then take the quotient by this large group in order to go through it. So of course it's very beautiful, but you know there's some way to go before you can use this to find anything about the metric itself. So is there a different approach you may ask? At least I think. Well, there is, and it's an approach that I actually used a long time ago. It's the Penrose twistor space approach. And so let me tell you what that involves. So this is another way of looking at hyperk manifolds. So now you take those, you look at the complex structures I, J, and K, and you take linear combinations of them. And if the coefficients are parameterized by the two-sphere, then each one of those is also a complex structure. So you take the product of your manifold M with the two-sphere of complex structures, and you can put on this a complex structure. Each point of the two-sphere gives us a complex structure in the tangent space of M. S2 itself is complex, and so it turns out that this is actually a complex manifold. And it has various properties. One is that if you fix a point on M, then the corresponding two-sphere is holomorphic. And if you project onto the two-sphere, then that's also holomorphic. So these P1s, these two spheres, holomorphic curves, we call these twistor lines. They're basically holomorphic sections of this fibration of the three manifold over the projected line. And if you look at these three symplectic forms, three Keller forms, you put them together and you, with coefficients which depend on the two-sphere, and that gives you a section essentially, well, you take the 2-0 part of it, it gives you a twisted, relative holomorphic symplectic form. So that means a holomorphic symplectic form on each of these fibers, which is twisted by O2. And on top of that, there's a real structure, this complex conjugation in that two-sphere, the antipodal map. So those give you this structure. So you want to construct the hyperk metric by using this method. Then first of all, you have to construct this twistor space. And that of course means that you need knowledge of all the complex structures parameterized by you. So, for example, if you wanted to try and use this for a K3 surface, then you already have to have some knowledge, some way of obtaining the complex structures on this full twistor family, the generic one of which is non-algebraic anyway. So, I mean, it has to be, if you want to use this method, you have to have a different way of doing it. But once you've found that twistor space, then the second problem is finding the holomorphic sections, which are going to give you the twistor lines. And then if you found those, then okay, you've got to really check that the ones you found have the right normal bundle, which should be a sum of O1s. And then it turns out that a certain component of the space of real twistor lines is the space, this is the underlying space on which the hyperk metric is going to live. And it's a relatively easy matter to actually find a metric. So in our case, of course, this comes, if you like, from Kronheimer. But on the other hand, it's the sort of thing which is kind of obvious if you look at it from the twistor point of view, but nevertheless, if you like, it verifies it because it constructs the metric. That the constructing the twistor space is not so difficult. So you take your singular surface that's given by well-known equations in 3 variables. So if you take the real invariant polynomials on the C2, it's generated by 3 x, y, z, various degrees, Ln and m. They satisfy the single equation, which gives you an embedding of this singular surface in C3. And this, so this singularity here has a versal deformation. So you add on lower degree polynomials, and the coefficients turn out to be basically violin invariant polynomials in the Cartan subalgebra type ADE. So if you like, so that now if you parameterize, if you take a basis for the Cartan subalgebra, then you're looking at a function of x, y, and z, and lower order terms, I'll give you an example in a minute, whose coefficients are polynomials, invariant polynomials in these entries here. And then you have the Kronheimer moment map. So then the point about these Cartan subalgebra is that you can in fact identify the algebraic center G with this Cartan subalgebra. So the choice, so I mentioned 2 different ways in which this parameters come in here. One is the periods, the second is the choice of moment map, and here it's this choice of something in the tensor without grid. So okay, so here's the 2 examples. Okay, so maybe you want to look at the examples first. So the AK ones, you see, we have the singularity is x, y equals z to the k plus 1. The right hand side now is product of factors, but the coefficients are symmetric functions in the PIs. The PIs here are actually functions of u. But if we look again at the EK case, we've got the coefficients we've got some symmetric polynomials in the PI squared, and then we've got this product here. So this is like saying, if you like, topologically, these things are like triagonal classes, and this is like a product class. The invariance is SO2. So anyway, so what happens is that this, you understand what the choice is. The choice is something in R3 tensor Cartan subalgebra. So that R3 you identify with sections of O2, real sections of O2 on P1. In other words, real polynomials in variable u. The reality here means this, the one that I've got there, that BI is real. We've got AI and AI bar. So that's because, if you like, the discriminant is 4bi squared plus 4ai guards, Euclidean product. So we have now the twistor space then is divided by x, y, and z and u. So this is the points inside this rank 3 bundle over P1, which satisfies this equation here. So that's, but of course, there are singularities when one of these PIs, the two of them have the same value at the point, then of course it's a singularity, and you have to resolve those. Okay, and there's questions about exactly how you resolve them, but the resolution is possible because you've chosen these actual coefficients in this particular way. So actually, writing down a candidate or writing down the twistor space or Kronheimer's examples is relatively straightforward. So what is the next problem? The next problem is really finding the twistor lines. That means finding polynomials. So we're looking at sections of this. So that means finding polynomials in one variable of the appropriate degree, which satisfy this equation. So this now is like a diagram problem. It's rather like having an algebraic equation with integer coefficients, and you're actually looking for integer points, rational points on the right. So that's quite challenging. But back in 1979, I looked at basically the 8K case. And I also looked about the same time at the case of the DK. But as you see, the publication date was like 25 years later. So what's the reason for this? Well, so first of all, in 1979, we didn't have Kronheimer. So we didn't have a solution, but in fact we did have a solution. So in the 80s, Stephen Hawking and Gary Gibbons gave us the metric. They gave us another formula for the metric, which was certainly not derived in this way. It wasn't derived by the hyperk quotient either. They simply wrote down an ansatz, and with that ansatz you could check that this was well defined on the space that it's supposed to be well defined and this asymptotically locally behavior. So I was in a good position then for this paper, Polygons and Gravitons, to actually produce a twistor version of it, because if you like, all I had to do was define from the twistor point of view the formula, and then check that the formula was consistent, and in fact gave the same formula as given to Hawking. The situation with the DK case was different. I found the formula much more complicated, but there was no way that I could fit it onto some pre-existing metric. I mean, I couldn't decide that it was well defined on such and such properties, completeness, and so on. Because whenever you got a formula with local coordinates and so forth, you can't really get hold of the global picture. So that's why I had to wait. So I put it in the drawer for 25 years. But then Cherkis and Kapustin were looking at hyperk metrics on modular spaces and monopoles. So by that time, we were looking at the infinite dimensional hyperk quotient construction, which was yielding, well, in particular, yielding hyperk metrics on Higgs model moduli spaces that we've been varying, but also on the moduli spaces of monopoles. And so it turned out that certain moduli spaces certain rank 2 or SU2 monopoles of charge 2 with singularities seem to agree. I won't go into it, but the spectral curve construction was compatible with the data that I had. So that's why this formula appeared only much later. But that's the E6, E7, and E8. I mean, thought about it a bit, but other people did, I'm sure, but it's a mystery. So that's really the motivation. Come to say something about E6, E7, and E8, and maybe shed new light on the other ones by doing a different approach. Okay, so before I do that, let me just say, so this is the way that, if we go back to the question about the Diophantine aspect, solving the equation with polynomials, this is how it goes in the simplest case of the AK case. So you want to solve this equation at the top there with polynomials, where Z is now a quadratic one. So all you do is you factorize each of these Z minus PIs into two linear factors, and you put half of them into X and half of them into Y, and then there's a scalar A that goes into it. There you've got it. So you have your three parameters for the coefficients of the quadratic Z. You have this A, you have your four parameters, and so you work out. Of course, you have to know how to put which one of the factors U minus alpha I or U minus beta I you put into X, which you put into Y. In principle, if you're looking for crystal lines in general, maybe lots of different pathways depending on how you do that. But in this case, because the discriminant of the real polynomial is positive, then you put the positive one, positive square roots on one side, and negative square roots. When it came to the decay case, that's more complicated. So you rewrite the equation like this, and then you see that this expression here, which involves now Z now is a quartic polynomial. And here you have a square root of Z. So what we can say is that this is actually a rational function. If you solve this, then you have a rational function on an elliptic curve that is squared equal to U with certain prescribed zeros and poles. And that's a constraint. It's a constraint on the 5 coefficients of Z. And so that's rather more difficult to handle. On the other hand, that's what led into the monopole picture, because if you, in the monopole picture, we're really looking at ALF space, asymptotically local flat, where the point was that the difference between the divisor class of the difference between the zeros and the poles of that function actually happens. Well, it won't be a function, but there have to be a given class in the divisor class. So anyway, that's why there was a link between special curve constraints and monopole in this picture. Anyway, that's a sort of, it's hard to do when you get the thing. So here's a more geometrical approach. I mean, it doesn't work in full generality, it works in the most interesting case. So if you look at the twistor space of R4, then as we heard from Pepe earlier, we can understand that as removing a line from P3, or we can think of it as the total space of O1 plus O1 is rank 2 bundle over P1. And if we have an ALE twistor space, asymptotically locally Euclidean, then what we have is we can compactify that. Out at infinity, it looks like R4 modulo gamma, and so its twistor space is going to look like this modulo gamma. So basically, there's an orbifold compactification by this projective line which you put in R4 modulo gamma. If you like, you can think of the R4 as having this conformal compactification to S4, and then the point in twistor space corresponding to the point in infinity is this P1. And then you can blow up the singularities. So you can blow up singularities of this orbital singularities, and you can do that all the way along, and you get a fiber-wise compactification of this twistor space here. So what you get is actually a compact manifold. So it's Z bar there, which fibers over P1. It's not K. So the reason for that is, well, you'll see a consequence of that. So the point is to kind of study this. And what is that compactification? So this is quite well known in the people who work with these singularities. It's an anti-canonical divisor with the right multiplicity. So here, this is for the EK type. So we have rational curves, E, F, G, and C. C is is in -1 curve. The others have self-intersection, like these numbers here. And then the anti-canonical divisor here is linear, so positive combination of these two. If you look at the other cases, so the AK case, well here, there's a reason I look at just the algebraic ones. Anyway, this is what we get in the AK case, and this is the DK case. So the DK case looks like okay, DK, but just got -2, -2, and -2. So this configuration of rational curves sits at infinity, if you like, on each of these fibers of the twistor space. So it's a substitution, if you like, for in the equation. So what have I done here? Here I've taken 6 points in the plane. I've put a conic. I've taken the conic through 5 of them. And I've got a 6 point here, which I want to be tangential to this conic at the points F. So if I blow up X, F, E, blow up these 6 points, then I've got a cubic, as well known. So 6 points, no conditions. I've got a cubic surface, which is actually the equation for D4. So I wrote down this equation for the versal deformation of the D4 singularity, and it turns out to be a cubic. Then the point is that when I blow up that point F, and so that's what I have to do to get the cubic, then I've got 3 lines. So I've got E, F, and G, the exceptional divisor of line from F. I've got E, F, and G, 3 lines meeting point, cubic, and that's a plane section, which is a tangential plane section meeting within 3 lines. And if I blow that up, then I get the configuration I've been looking at there of the D4. So it's easier to look at this. So what I'm saying now is that actually if I blow up further points, depending on what I'm interested in, then I get a complex surface, projective surface, which has that same configuration of infinity. So my generic fiber in my twistor space is going to be one of these surfaces. So all the parameters are there. You have these different points and so forth. So instead of having an equation for each fiber, I use a surface, a smooth projective surface, and the fiber, the genuine fiber on which the metric is going to be defined, is obtained by that, where I remove this divisor. And incidentally, the cubic surface you get by this construction, this is the one where if you put the right real structure into it, you get the real cubic where it has a 2 components where one is compact. And so this is why when you have you look in cabinets of well-established mathematical institutes who have these plaster models of certain cubic surfaces, you never see this one because they have to suspend something in the air. Okay, so here's where we restrict things slightly, but make things more interesting. And we look at ones where there's a circle action. So we want to look at the circle action which starts on C2, and it's just rescaling C2. So this acts on the resolution, and it acts on the twistor space. Well, we have to choose the right moment. So if you, so this is going to be a circle action on the hyperk manifold, which fixes the complex structure I and rotates J and K. So those of you who are looking at, say, Higgs random moduli spaces, this is exactly the same sort of circle action. So it fixes, if I think of 0 and infinity in P1 as being 2 points, then this circle action acts non-trivially on the basic P1 and the fixed points are 0 and infinity. The fibers over those points in the twistor space are the resolution and its complex conjugate. The general fiber is an affine surface whose completion is one of those surfaces I've just described, or you blow up these points along the horizon. So, okay, so here, this is what I'm saying, that this is the action on the twistor space. So, in order to get that, we need the circle action. We would need a moment map, which is where you can set the JK terms to be equal to 0, and you now have just the parameters given by the first map. So you have K real parameters now. Yeah. So, okay, and so this is a picture. So now we have this twistor space, Z over P1, that's what I've just been saying, we have 5 over 0. I'm just taking now a 5, I'm choosing a point, let's say U equals 1, some point in between 0 and infinity, and I look at the fiber over there. And its compactification is one of these projective rational surfaces that I've just been explaining, which you can get just by blowing up some points in a specific way on the plane. So what the aim is this. So we're looking for twistor lines in the twistor space. The idea is to kind of project such a line onto Z1 bar, onto this rational surface. What do I mean by project? I mean, take a twistor line, transform it by the C star action. I get a surface, and let me look at its closure. I get a closed surface. That's going to intersect this surface Z1 bar and the curve. So each twistor line will generate a curve, rational curve in Z1 bar. And we have a 4-parameter family of twistor lines. And if we forget about the real structure, we have a complex 4-dimensional family of twistor lines in the actual twistor space, but we're looking at C star orbit. So what we hope to get is a 3-parameter family of rational curves inside this projective surface. So let's just see what properties these curves will have. So first of all, let's again look at the case of that space on core. So here we have the twistor space. Direct sum O1 plus O1 over P3, so it's P3 minus the lines at 0, Z1 is 0. And the twistor lines are just given by, of course, a pair of linear functions, which like this. And here's a C star action, and the C star orbit, you can just eliminate lambda, and this you see that you get a quadric surface. So the general quadric surface, it's a quadric surface, and it meets the line at infinity, of course, in 2 points, and there's a degree of freedom there in those 2 points. So the twistor lines from in flat space, they generate a surface, which is a quadric surface, and the property that it has is that it meets this line at infinity in 2 points. So for an ALE space, then this projected curve that I'm talking about is going to have one property at least, which is to meet the C. So that C, that -1 curve, is basically the blow-up. It's the corresponding curve of that P1 that I had before. So that's a piece of data about the cohomology class of these rational curves, but not sufficient. Now, so let's look at now the points over 0 and infinity. So now the action, C star action preserves 0, so it acts, of course, on the resolution, that's what we started on, and it acts on this whole configuration. But in particular, this central curve, this trivalent vertex here, well, you can't have a C star action on P1, which has 3 fixed points, unless it fixes every point. So unless it's 0. Right? So that point, that curve C0 is actually pointwise fixed. The action on the other points, they just have they fix just a pair of points which correspond to the points of intersection with P1. So this, if you like, again, for those people who like the Higgs bundle moduli space, this central curve, the fixed point of the circle action, this is like the moduli space of stable bundles sitting inside the Higgs bundle moduli space. It's right at the bottom. So, that has a special role, that central curve. Now, the twistor lines, in full twistor lines, are sections of this P1. So, in particular, there's a real twistor line, at least through every point of Z0. The real twistor lines are the ones which identify this with a product, C infinity as a product. So we're going to look at this C star action. If we look at the flow of the C star action on the resolution, the space of the resolution, then because generic twistor line meets it, there's one that meets it at every point. So if you flow down, right, you have a C star action, flow down, and the generic one is going to go all the way down to C0. Some of them will hit the other fixed points, but that's sort of lower dimension. This is like what we call the upward flow in the Higgs bundle moduli space. The C star action. If you take a fixed point, some things go up, but some of them go down. It's like saying that the generic underlying vector bundle in the Higgs bundle picture is stable, and so the C star action goes right down. So what that means is that if we take a generic such twistor line and do the projection, then the closure of the orbit is actually, it intersects, the only thing that it can intersect are C0, which we know intersects in 2 points, or C, which is the one at infinity, and this C0. So it flows down and hits 0. And so we have this. So this picture, in fact, this method appears in this earlier paper of mine, but I won't mention much about that. So what do we know? We know that the intersection number of the cohomology class of S and C is equal to 2, and we have this family impact surfaces. And we have this round family of surfaces. The intersection of this curve C0 is greater than equal to 0. On the other hand, we can look at the other end. We can look at the C infinity. So so the same thing happens there, except that the C0 is then, it's got the complex conjugate structure. So this is when I said that these twistor spaces are not Kähler. Here is one reason, right? If they were Kähler, if you had to take a Kähler form, you evaluate it on C0 one end, and you get something positive. But if you look at the other end, you'll get the opposite, but with some different orientation. So we have anyway. So that proves, if you like, that this is not Kähler, because this same C0 has a holomorphic curve inside. Represents a holomorphic curve with opposite orientation. But in our case, what it means is that the intersection number is actually equal to 0. So now we've got the situation where we know what the property is, that there's a cohomology. So these intersections here, we can say one bar, the cohomology class has the property that its intersection with this curve at infinity is 2, but it's trivial on the image of the homology of the open part. Z1. The part is generated by these twistor. So that's quite a significant constraint. So these things are trivial. They don't intersect with that. How do you use that? Well, you just you try, if you like. If you look at, we know that C, E, F, and G are trivial on H2. And so you just try a linear combination of C, E, F, and G, which satisfies these constraints, and this is what you get. So, so these are divisor classes which have the property they want, that the intersection with C is equal to 2, and the intersection with all the others is equal to 0. Now, if you look at this, you can evaluate certain things. So if you take the intersection of the canonical divisor, you get -4. You find that, just by evaluation at this point, that Q squared, the self-intersection number, is the order of the group, it's gamma. So right at the end, I'll try and give you one explanation. So now we need the adjunction formula, so that K equals Q squared is 2G minus 2. And we know we've got a rational curve, that's projecting basically a rational curve. And so we deduce that it's got a lot of nodes. So we didn't know in advance that this was going to give us a nodal curve, but it's going to be does. And so what can we say here? Well, here's, I'm quoting a theorem here. If a smooth projective surface has a rational curve C, which has this delta nodes, with all the singularities, and this property holds, then the variety of such curves are non-singular. So this is a theorem about deformations of nodal curves in any surface. In our case, you see Q squared is this, so you'll see what happens. What we find is that the number of non-singular curves, so the variety of curves is non-singular and in 3 dimensions. That's exactly what we get by doing this projection. We started with a 4-dimensional family. We did this projection, we got a 3-dimensional family. Generic number of that 3-dimensional family satisfies its constraints. And then an arbitrary deformation of that is going to be the same 3-dimensional family. So these curves then are the curves. So the curves we're looking at are actually the curves in this linear system Q, which have this number of nodes. So this is so this of course is a difficult problem. Algebraic geometers, I'm sure will know that if you have a particular linear system and you want to identify all the curves within a linear system which have a certain number of nodes, I mean nodes which move around, which are not necessarily fixed, then that doesn't make life any easier perhaps than solving that Fantine type equation. But nevertheless, it's a geometric way. So here's an example. So the AK situation. So in this case, we've got a different kind of, slightly different magnification, but the obvious way to produce this is to take the projective bundle of O plus OL, and then blow up 2L points on the AI and the 0 section, and that gives you a 2 minus L curve in it. So the C there is a fiber of this vibration of P1. So we want QC to be equal to 2. That means that we're looking at something which is has degree 2 as a projection of P1. So if you like, you can write it down this way. We'll use, it's like an academic term almost. But we've got it's got to pass through these AI points, these 2 AI points. So C2 is basically fixed up to the constant. And now you want this to be nodal, so now you want this point nodal here, something like 0. So that's geometric, but again, as I say, it's not necessarily as easy as just factorizing things that we did at the beginning. Here's another example, D4. This I said was a cubic. So what are these curves here? Well, basically they are quadrants. If we look at the cubic surface inside P3, smooth cubic surface, you have this particular point where the plane makes it in three lines, and then if you look at the quadrics to that point, which are tangential to x, then that's the system that we're looking at, but we require them to have three more nodes, and the nodes are the twistor lines in the important case. Okay, so we have this is the theorem of Honda and Macanta, and so this is the paper that occurred in, and as you see, there's some other words in the title. You've got Severi varieties, so those are the varieties of nodal curves in the linear system. But you've also got a statement about many twistor spaces and Einstein bias. So I'm going to move now. So I started with differential geometry with hyperk. It's an algebraic geometry, and now coming back to some differential geometry. So you may not know what an Einstein-Bauer manifold is, so here's what it is. It's a manifold with a conformal structure and a torsion-free connection preserving the conformal structure. So the easiest way to do that is to choose a metric within that conformal equivalence space, and then it's given by so that the Riemannian metric, of course, preserves volume form. A general conformal one doesn't, but it has a connection on the bundle volume form. So basically, I think Weil was interested in incorporating the electromagnetic field into general relativity. This is an attempt to do it. So two forms, okay, d omega, the curvature of the connection on the volume bundle was supposed to be the electromagnetic field. It didn't work out, but it's just the geometry that was there. And Einstein-Bauer, so if you look at the Ricci tensor of one of these, you can still construct a Ricci tensor. It's not automatically symmetric. In fact, the skew symmetric part is basically the curvature of the volume line. So the Einstein-Bauer manifold was one where the symmetric part of the Ricci tensor is scalar. So you have the Einstein condition on the symmetric part. And the important thing from that point of view is that if I take the quotient of a hypercalar form manifold by a circle action, then I get an Einstein-Bauer thing. So that's what the link is in this situation. In fact, if you take the quotient of it's far more general than this. If you take the quotient of a conformal, self-rule conformal form manifold by circle action, preserves the structure, then that is also an Einstein. As a matter of fact, the actual equations that do, there's a very natural way of writing the equations. So this is a little on the side, but I thought maybe I'll put it back in there. But we have this, if we have a hypercalar manifold, like the one we have, like an LE space, with circle action, then you've got a moment that corresponds to the circle action for the Kähler form under the one. And then you can take a Kähler quotient, say the inverse image of T with respect to that movement, y in the circle, and then you get a surface with metrics. And it turns out that there's another metric on the underlying space that evolves according to this second element. It's hardly evolving, it's like a wave equation and a heat equation. But if you take just the Gaussian curvature and solve this equation with certain initial conditions, then that's equivalent to actually finding this, describing this Einstein-Bauer structure. So if you solve the equation, well, okay. In our situation, the circle action has a fixed two-sphere, and there's if you take the initial conditions equal 0, then this is what you get. So I don't call this initial, but there's a good way of doing it. And okay, so this structure was looked at first by, well, obviously by Weil, but in particular by Kalkstein. And then, okay, so then I came on it in the early 1980s, and then it was developed a bit by students, not to. So here was my take. So it was a miniature version of twisted, so mini twisted. So the point was that if you have a complex surface with a real structure, and you have a family of rational curves of self-intersection 2, and then the space of real curves has viral structure. And the point about this is that the surface S is the space of oriented geodesics. So you have this complex surface with its family of P1s.
Yes. Good. And this is the person. Oh, sorry.
Sorry.
No.
I'll say. So this is supposed to be, so at each point of this complex surface, well, if you look at the P1s, if you look at the P1s through a point, then these are the oriented geodesics. Anyways, so the fact that the self-intersection is two of these intersect in one point. I mean, so two of them intersect in 2 points. That's equivalent to saying there are two oriented geodesics joining two points in space. And so, okay, the standard examples here were the total space over 2 over P1, which is obtained by dividing out O1 plus O1, which is the space of R4 by an action, not a singular action, but a translation action. And that gives you the flat R3 and the quadrant here, if you divide out, you get this hypermodal space. So my reason for doing it back in the early 80s was to have the right setting for solving monopole equations, bottom-only equations in 3 dimensions. So bottom-only equations correspond to the whole bundle on this total space and this twisted space, and likewise in this case. But the point about this was that if you ask for your surface to be an open set in a compact complex surface, then of necessity, the local structure of this Einstein-Gauss space is just going to be one piece. So at the time, it seemed like it wasn't going to interact, if you like, with genuine algebraic geometry in a good fashion, and but it was a good background in monopole. So what Honda and the company did is to say, well, actually, if they have this condition of self-intercept become now a curve with nodes, and then certain properties, then you can kind of normalize the Euclidean neighborhood in which the normalized curve actually has self-intersection too. And then you can see that this is like a mini twisted. So the local structure is compatible with the structure I have, but there's a local structure because you're looking at these nodal curves. So the nodal curves themselves are sufficient to generate this structure. And so here, let me give you. So here's the first. Okay, the first example here is A1. So this is where the ALE space is the cotangent bundle P1. The resolution of the singularity is just the zero section of the cotangent P1. So this even predates Gibbon talking. It's called the Ruchi Hansen. And in this case, okay. Gamma is plus or minus 1, so in fact we have smooth twistor counts in this case. The number of nodes is 0. But here, if you like, with my model, my model is this. You can see the total is the -1 picture. So it's really blowing up 2 points on this configuration, but if you blow down the -1 curve, you get P2. And now we're looking at conics in P2, which intersect that line C in 2 points. So that's basically saying, yeah, so we're looking at curves in P2, which intersect the line in 2 points. So with the conics that pass through 2 points, you blow up and blow down, and see that there's going to be 1 curve and P1. So if you like, we reduce from algebraic geometry that the quotient of the Cauchy-Hansen metric by the circle actions is, well, you know, if you look at it that way, okay, that's interesting, but you can actually check it. You have to check it. So that's another formula for the Cauchy-Hansen is fair hyperbolas. But yeah, you make the right substitution, and you can see that that's true. But what it does tell you is that actually the two things. One is that the resolved singularity is now, of course, the zero section of well, it's the zero section of this cotangent one, and then that becomes the two-sphere infinity in hyperbolic space. What happens to infinity in the ALE space? Well, that just becomes a distinguished point in the hyperbolic two-sphere. So the difference of so we have this two-sphere, which is finite in the ALE space, that becomes infinite in the Einstein-Wild space. And so what happens in general? In general, well, you can say that the quotient, I think I'd like to say that it's Poincaré-Einstein-like. So a Poincaré-Einstein metric is usually defined as a metric on a manifold boundary which satisfies Einstein's equations on the inside, and where it blows up on the boundary, but the conformal structure extends over the boundary. Rather like hyperbolic space itself. You have a constant negative curvature, complete constant negative curvature on the interior of the ball, but the conformal structure extends. And in fact, so that's the property that these particular solutions have. That the conformal structure extends over this two-sphere of infinity, but the formal connection doesn't extend necessarily. Of course, they're not actually manifold because we have fixed points of the circle action. In particular, we have these orbital singularities at the points where the resolution intersections of those two spheres. And in particular, at the infinity in the ALE space gives you an orbital singularity at a distinguished point, which is looks like R3 modulo the subgroup of the bottom group. So let me just finish by kind of giving you a geometric explanation of why this self-intersection should be given by the number of elements in the group gamma. So what I did was just kind of work it out in those formulas. But using this Einstein-Wild picture, you can understand it in terms of some geometry. So what does it mean? It means that there should be this number of oriented geodesics between two generic points. If we understand points in the surface as being oriented geodesics. So we have an orbital. So suppose we have a fundamental domain and we pair so with the action of gamma over one, then we could take one geodesic, we take one point in there, a pair of points in this fundamental domain. And then we can move one of them out there, we can move it out there, and so forth. And so we get, so these are unoriented geodesics, so that's what this is counting. So depending on, so the orbit is that second one there, by the scatter, it's not gamma. So there's if you like a geometrical reason. Yeah. So that's the story. What is it good for? Well, it's probably not good for actually finding any explicit formulas for the metric. What it might be good for is this. What we know is that if you look at instantons, ALE space, then there's a moduli space which was initiated by Kronheimer and then carried on, well, initiated by Nakajima, and carried on by the pair of them. And it led to these Nakajima equivalent varieties. There's an AVHM construction. And so what we're looking at here, if we look at from this point of view, what we can say is that an instanton which is invariant under the circle action is the same thing as a monopole on this Einstein Laurent space. And now, how do you describe monopoles? Well, of course, if you have a matrix, an ADHM configuration, and if you approach it from the point of view of ADHM, then you could say, well, I put in the circle action, it'll break it up into pieces. You have, instead of having matrices, you have a lot of matrices. And that is an approach which was done a long, long time ago by Brahm and Austin and so on, but I never felt that it was very helpful. Instead, there was an approach to monopoles in Euclidean space and hyperbolic space in terms of spectral curves inside the mini twistor space. So what I feel is that there's a way of describing the fixed points, the circle action on this Nakajima quiver variety in terms of some curve data inside this surface, this rational surface. We have these twistor lines which are nodal. I don't know what the conditions are. Of course, there are all sorts of ways in which it differs from the standard case of R3 or hyperbolic space. But it's possible that there's a way of describing these fixed points in these instanton moduli spaces in terms of curves inside this rational surface. And that would be a nice conclusion if it doesn't get too complicated. So I would finish.
So you mentioned in the end the instantons on the ALEs. If people consider the holomorphic bundles on the twistor of these ALEs, and how does it go for this compactification that is not scalar?
Well, it's true. That's a good point. Forget the non-scalar twistor space. That's true. On the other hand, how should I put it? I mean, we do have a matrix description. There's a how will this non-colorless really interact? I mean, what we would want is a holomorphic bundle which is triggered on the real twistor lines. How important would it be to know what it is on these other predicted lines? Since we know that we already have a description, I don't think we need to go back so far and try and go to the basic constituents, the cohomology, the twisted below lines, whatever it is, and interpreting that. But it may be possible. I don't know. So my view is that an ADH type construction is very good, and of course they also can understand the topology of these moduli spaces where you have some framings. I think they have framings, so they have not just this circle action, but some more circle actions, and then they can look at its point points and so on. But that's kind of counting things and generating homology. So I'm not so much thinking of going to how you derive a particular construction of the instanton. I thought maybe just taking what's given and trying to interpret what's given, perhaps in terms of data on this rational stuff. But in principle, one ought to start by saying, what does it mean? In case these mini twistor lines were smooth, you would say you want a holomorphic bundle which is trivial on the surface, which is trivial on the rings. What do we ask for here for the nodal? We want some free sheet, torsion sheet. What conditions do they going to satisfy? It's not, at first sight, it's not quite clear what to do. On the other hand, at least for the SU2 monopoles, and this was, somehow the model of Attia's work on hyperbolic case, monopoles in hyperbolic space, and spectral curves in P1 plus P1. I think you can look in the kind of four-dimensional picture. You can look at the jumping curve, the divisor of jumping curves. I think this the spectral curve is related in one dimension higher to the jumping curves, the twistor lines on which the vector one is not triggered. So I think one could immediately kind of transform that into this picture and then ask questions about whether anything is determined by that. I think there are a lot of issues there which really too complicated with that.
Yes.
There was just one thing that confused me. So the surface which you were speaking of that was non-Kähler was the closure of an orbit.
No. The non-Kähler was the full three-dimensional crystal space.